Now let's talk about remote and distributed visualization. If your dataset is sitting on a cluster and you want to visualize it, you have actually quite a lot of options. One of the easiest options would be to simply download the dataset to your desktop and visualize it locally. So if it's a small dataset, let's say a few megabytes, then you can do that very easily. If the dataset is large, if it's multiple gigabytes, tens of gigabytes, then downloading to your laptop will actually take a very long time, and it might not even fit into your laptop's memory. You might not even have enough CPU or GPU processing power to process and render this dataset. So for example, if you're looking at a numerical simulation and each time step of output is 80 gigabytes large, then you obviously cannot load it into your laptop or your desktop computer because you typically would need more than 100 gigabytes of memory just to process and visualize this dataset. So the next option would be to use X11 forwarding. You can actually SSH to the cluster with either -y or -x option. So I recommend doing SSH -y and typing a username at the name of the cluster. And this way you can open graphical applications on the cluster and see the windows from this application on your computer. So to enable this, you need to have X11 server. So X11 stands for the windowing system on Unix. You need to have an X11 server installed on your computer. And there are X11 servers for Linux, Mac, and Windows. So while this method will work, I really discourage you from using X11 forwarding, simply because it's going to be very slow and your experience will be rather miserable. So X11 forwarding was developed in the mid-1980s, and it was never designed for such graphics-heavy applications as ParaView. So while this will work, it's just going to be very slow. So when you click on a button, it might take multiple seconds for ParaView to react, etc., etc. The next option is to run ParaView remotely on a larger machine using some sort of remote desktop software such as VNC or X2Go or something else. On Compute Canada clusters, we support VNC and X2Go. Let me open the web browser and I type docs.computecanada.ca. This will bring our main documentation page, and if you search for VNC, it will give you a long page with several options here. So one of the options would be you can start an interactive job on the cluster, and then inside this interactive job, you can start a VNC server, and then you can connect to this VNC server from a VNC client on your computer. And this will give you a graphical desktop. And then inside this graphical desktop, you can open Windows, you can open a terminal, and then open a ParaView window, etc., etc. VNC or X2Go will be faster than running ParaView through X11 forwarding, but it's also not the best option. And I honestly don't recommend using VNC for ParaView because there are much better options. So the two real options that you should use is either running ParaView in client server mode or running ParaView in batch mode. If you remember, when we were talking about the ParaView architecture at the very beginning, I mentioned that ParaView has a client and a server inside the ParaView application. So the idea is that you can run a ParaView server on the cluster, perhaps in parallel. Then you can run the ParaView client on your computer, and then you can connect the two, and you have a very nice interactive visualization experience. You will use client server mode if you need interactive visualization with the GUI. And if you already scripted your visualization, you're simply running a visualization script, and then you can just run the script as a batch job on the cluster. Now, there's a special case of in-situ visualization. Just to remind you, in-situ visualization refers to instrumenting your code to output graphics, or perhaps doing live visualization while the simulation is running. And in-situ visualization is really a much more advanced topic than what we're covering in this course. So if you're interested in in-situ visualization, please let me know, and we can try to organize special webinars on this topic. Now, you already know that the general purpose clusters in Compute Canada are Cedar, Graham, and Beluga, and all of them have ParaView installed. And we also have Niagara cluster at the University of Toronto. So Niagara, unlike Cedar, Graham, and Beluga, is meant for very large parallel jobs. And on Niagara, we have ParaView installed as well. In order to use ParaView interactively on the cluster, you will need to start an interactive job using salo command. And here in this example, I'm asking for 1 hour maximum runtime for 4 MPI tasks. And you probably need to specify your count as well if you have more than one allocation. For example, if you have a rack allocation and a regular queue allocation, then you would have to specify which allocation you're going to use with this -- account flag. On each of our clusters, we have a special interactive partition, and you can actually list the nodes in this interactive partition with this command, type as info, and then pipe it searching for interact. And this will give you a list of nodes and their states, for example, idle, mixed, allocated, etc. So as long as you have some idle interactive nodes, you should be able to run an interactive job. An important question when you're trying to do rendering on the cluster is whether you should use CPUs or GPUs for rendering. Common sense tells us that GPUs were designed for graphics, so they stand for graphical processing units, and they should be really fast. So GPUs have traditionally been faster for rendering graphics. However, the situation is not that simple. In recent years, we saw development of very fast software rendering libraries, such as Osprey, that's the Intel's ray tracing library, and OpenSWR, which is the Intel's rasterizer library. And they have largely closed the performance gap for many different types of visualizations. If you're just starting doing visualization on the cluster, I really recommend to use CPUs as opposed to GPUs. And the main reason for this is on an HPC cluster, we don't have a lot of GPUs. So typically CPUs outnumber GPUs by a large factor, something like a factor of 30 or a factor of 50. So that means that you are much more likely to be able to reserve a CPU as opposed to GPU. In fact, you can throw a lot of CPUs at your rendering job. If you have a large data set, you can start an interactive job, let's say asking for 32 or 64 CPUs. And then from these 64 CPUs, you'll be able to read your large data set in parallel. So your read time will be much faster compared to when you were doing this from a single processor. And now, because you already have 64 processes to read your data, apply various filters, why not use the same 64 processes to do rendering? And this will be actually much faster than using one or a few GPUs. So on the cluster, because we have so many more CPU cores available as opposed to GPUs, and GPUs are just in very high demand, it really makes sense to try CPU rendering first, and then maybe you want to experiment with GPU rendering later on. The second question is, how many CPUs should I use when I try to render a large data set on the cluster? In my experience, the rendering speed is really a small issue. So much bigger issue is the amount of physical memory that you have, because if you want to load a large data set, then you need a lot of memory, and also disk I/O speeds. So in order to read a large data set, if you're doing this on a single processor, let's say you're trying to read an 80 gigabyte data set on a single processor, well, it will take you maybe 1, 2, or 3 hours to do this, because 80 gigabytes is a lot of data. If you're reading this data set in parallel using, let's say, 64 processes, and then you're loading it into memory on 64 processes scattered across some number of nodes, it will take you only a few minutes to read this data set. So as you can see, just the fact that you're using a lot of processes and you're reading data in parallel will reduce the dataset reading time dramatically. And now, because you have a lot of processes, you have access to a lot more memory, so you'll be able to fit your dataset into memory fairly easily. In order to calculate how many CPUs you need to use, I really suggest to look at the dataset size. As I mentioned, on CEDA, for example, each base node has 128 gigabytes of memory and 32 cores. So that is essentially 4 gigabytes of memory per core. You probably need to subtract some memory that is taken by the operating system and various utilities. So for example, 3500 or 3600 megabytes per core is a good starting point. So let's say you have an 80 gigabyte data set, and here we're talking about a single timestamp, right? So at any given time, you're trying to load a single timestamp into ParaView. So you're trying to load 80 gigabytes of data at once. And then if you take 80 gigabytes and divide it by 3.5 gigabytes per core, you will see that you need 23 cores to fit this data set into memory. However, you also need to account for various overheads, so for MPI buffers, for data processing, so when you use a filter that increases the memory footprint of your rendering and visualization. Perhaps you're converting structured data into unstructured data, and so on. In my experience, if you're trying to load 80 gigabyte data set on CEDA, you probably need at least 32 cores, but you should really be comfortable processing this data set on 64 cores. So I hope this gives you some idea of how many processes you need to ask for when you try to load your data set into an interactive client-server ParaView and try to process it interactively.